Yeah, so maybe let me first refresh your memory of what we did last time. So last time we looked at two algorithms for finding the ground state energy. One is the textbook version of quantum phase estimation, which works with an imperfect initial guess, but requires many qubits. And also we had this Hartman test, which can get you ground state energy using a single N0 qubit. But it requires a perfect initial guess. And both reaches the Heisenberg limited scaling. And we had a question at the end of the talk, like, can we actually have all the good features, which is using an imperfect initial guess and a single N0 qubit, and still reach the Heisenberg limited scaling? And this time, I'm going to present such an algorithm. So the main idea is to compute the, actually the motivating idea is to compute the spectral density associated with this Hamiltonian. So last time, one of you raised this question, like we got many examples from running QPE. Can we use them to like get information beyond just the ground state? Indeed, you can. So this is what we're going to do next. So here, let's say the Hamiltonian has eigenvalues lambda 0, lambda 1, all the way down. And for simplicity, we assume the spectrum is contained within this interval. So it might look a bit arbitrary to you, but but this is actually necessary. So it's contained in the interval between minus pi over 4 to pi over 4. And by spectral density, I mean that first we have an initial guess phi, and it induces a probability distribution over the spectrum. So basically, you can define the spectral density to be a linear combination of these shifted Dirac delta functions. So basically, your mu x will have a 2 to the n many peaks. Each peak corresponds to an eigenvalue of the Hamiltonian. And these peaks are weighted according to this pk, where pk is the overlap between your initial state and the case eigenstate. So we can interpret it another way. So say we draw a random variable x from this spectral density, then x will be equal to lambda k with probability pk, where pk is overlap. And all the pk sum up to 1. This is because phi is normalized. So that's why it's a probability distribution. So this is what we're going to focus on for the next few slides. This distribution contains all the information about the spectrum because you only need to find all the peaks in order to find all the eigenvalues. But you won't want to do that because that requires like finding 2 to the n many eigenvalues, which is basically impossible. And the Hartman test circuit can help us compute the spectral density. So this is Hartman test circuit we had seen from last time. So we start from approximate state 0 and phi. Phi is the initial guess, Hartman, control time evolution, Hartman measure, right? And what it does is that it gives us the expectation value of e to the minus ith with respect to phi. So we did this last time, which is writing down writing down the eigen decomposition of h and plugging it into here. What we get is we get a signal as a function of t that is oscillating, whose frequency is determined by the eigenvalues of h, and we have those pk's for the weight or the Fourier coefficients, as someone among you commented yesterday. So indeed, we interpret it as a Fourier transform, right? So so basically, your mu of x is just a bunch of Dirac delta functions. So instead of writing this summation, we can write it as an integral from minus pi to pi, and mu of x is spectral density. And so here we can replace this lambda k with x just because we're using this spectral density that is defined from this lambda k and pk. Any question at this point? Okay. Yeah. So that means we can reinterpret the result from the Hartman test circuit, which is we are actually computing the Fourier coefficients of the spectral density mu of x. So a natural idea is that okay, we have the Fourier coefficient, right? Let's just reconstruct the whole distribution from the Fourier coefficient. But it's not necessary. It's not really practical because we can only run Harman tests for a finite number of times, and each time the t needs to be finite because the cost grows linearly with t. So, and mu of x is a linear combination of Dirac delta functions. So if you look at the Fourier coefficients, they don't decay. They just so you will need like basically infinitely many examples to resolve it accurately. So what we do is we consider a smeared spectral density. So mu is our spectral density. We take the convolution with a modifier or a kernel. So this modifier is a smooth function, and so the convolution is written in this way. So after you take convolution, you will get something that is also smooth. And so then we can think of estimating the Fourier coefficients corresponding to this smooth function.
But wait, that's not enough. It has to integrate to 1. It has to be positive. Right?
Sorry, which?
The modifier has to integrate to 1, and it needs.
Yeah, exactly. Yeah, it has to integrate 1. Right. Yeah. So, but that's to ensure that your mu this mu tilde x approximates mu x, right? In order to, if we want to do that, we need to make sure that m is integrates to 1, and also it has to have some concentration property, which I'm going to talk about next. Because this is a convolution, the Fourier coefficients are related in a very natural way. It's just a multiplication between the Fourier coefficient for the spectral density and the Fourier coefficients for the modifier. So these Fourier coefficients, mu k hat, can be computed from Harman test, and mk hat are something we design. And because this mx is a smooth function, they decay very fast. So that's why we can use a finite number of examples to resolve the whole thing. And so there are several restrictions for m of x. First is because we only want to use discrete Fourier transform, right? So that means the kernel mx needs to be a 2 pi periodic function, and we actually want to be able to just truncate the Fourier coefficients so that we want there to be only finitely many non-zero Fourier coefficients, and therefore we require m of x to be a finite degree trigonometric polynomial, and as observed by it needs to integrate to 1. Yes.
Why not just use a Gaussian or something if you're trying to smear it, right?
Yeah. You can definitely just use Gaussian, but you then need to truncate it, right? There's a truncation error you need to analyze. Yeah. So here I'm just being lazy, so I don't want to truncate it. I just directly design something that is finite. Yeah. So in this 2020 paper by Lin and myself, we proposed such a function which is based on Chebyshev polynomials. It looks like this. There is a normalization factor which ensures that it integrates to 1. And it looks like this. So basically, you can see it's concentrated around the interval, at the interval around 0. So the length of the interval is on the order delta. And outside the interval, there is some fluctuations shown using this blue curve. And so with degree 20, you can see it's oscillating. But if you increase degree to, say, 40, then basically you cannot see any oscillation because it's roughly just 0. So the oscillation is on the order epsilon. And you have some target delta and epsilon you want to achieve. And then the degree of the kernel function will scale like delta inverse times log epsilon inverse. So that's roughly how many Fourier coefficients you need to estimate, which corresponds to how many Harman test circuits you need to run. This kind of function can be used to solve the quantum eigenvalue estimation problem proposed in this 2019 paper by Rolando Soma. So Rolando Soma proposed an algorithm that well, this is a problem he defined, but you can modify the problem so that it gives you the ground state energy. And so with his algorithm, you can get ground state energy with this kind of runtime. So we first assume there's an overlap between phi, the initial guess, and the ground state, which is lowered by some eta. And then the total runtime will scale like epsilon to the -4 times eta to the -2. So this you may not be very impressed by this scaling, but the good thing is the circuit depth is epsilon inverse. So if you remember from last time, the circuit depth for quantum phase estimation is epsilon inverse times eta inverse. So the circuit depth is actually better than the textbook quantum phase estimation, and it uses a single Anzilla qubit, and also uses an imperfect initial guess. So you can see this algorithm actually achieved two of the things we want to achieve, which is single Anzilla, imperfect initial guess, but the total runtime is too large. So the epsilon to the -4 comes from, so basically we need epsilon inverse many terms in the Fourier expansion. And in this algorithm, you evaluate each Fourier coefficient one by one. That means there are epsilon inverse many of them. So there's epsilon inverse overhead. And in order to evaluate a sum to precision of order eta, you will need epsilon to the -2 times eta to the -2 many examples for each term, right? Because this is just Monte Carlo error. And the average cost for each term is epsilon inverse because this is how long you need to evolve your system. And you multiply everything together, you will get this cost. So it's epsilon to the -4. And so here, this is the smeared spectral density they compute from the algorithm. So you can see those peaks, which are, so if it's just a direct delta function, then it's the original spectral density, but it's not exactly direct delta function. You have some kind of smoothness going on. So that's some kind of smeared spectral density they compute. And there are a couple of related works appear around that time, some of the others may be here. So and so they're all based on this Harman test circuit, and but this is the kind of runtime you need in order to achieve the target precision. So we call such an algorithm early fault-tolerant quantum algorithm because it has some nice features, which include like it uses only one Anzilla qubit instead of a bunch as in textbook QPE. Circuit depth is epsilon inverse rather than epsilon inverse times eta inverse. And there is some degree of noise robustness, which I will talk about at the end of today's lecture. And the early fault-tolerant algorithms are the ones that take the above factors into account besides the total runtime. We still care about total runtime. And that's what I'm going to optimize next. So there was a question? Yes.
Yeah, I was wondering why the precision would depend on the overlap in the previous slide.
Yeah, so, okay. So you see those peaks, right? So like let's say this peak corresponds to the ground state energy, right? Then you need to be able to resolve it, right? And how high is this peak? The peak is roughly on the order eta. So you need the noise to be lower than that in order to resolve it. Yes. Right. Any other question at this point? Okay. Yeah, so there is actually some inefficiency in the procedure I just described. So there are several observations that led to a better algorithm. So first, it may not be the best strategy to compute the smeared spectral density. It's simply because like you may be resolving those peaks one by one, and each peak corresponds to an eigenvalue. That's good. But we only want the lowest eigenvalue, right? So when we have an eigenvalue, we don't necessarily know what it is. Like, is it an excited state or is it a ground state? So that will compel us to compute multiple eigenvalues, take the minimum, and that gives you overhead. And so this is the first observation. And second, in the previous algorithm, we were evaluating each term one by one and then summing them up. So there are epsilon inverse many terms, and each of them takes epsilon inverse time to compute on average. That gives you a cost at least epsilon to the -2, which precludes any possibility of reaching the Heisenberg limit. But we don't necessarily have to do that because not all the terms are equally important. Like some of the Fourier coefficients are just really, really small. And if you compute them to high precision, that's actually a waste of time. So I'm going to use all these observations to propose a different algorithm. So in this algorithm, instead of computing the spectral density, I will compute the cumulative distribution function of that density. So the C of x is defined to be an integral of the spectral density. And you can write it down in terms of the Heaviside function. So we just, because like originally this Heaviside function was the direct delta function in mu of x, right? If you integrate it, you will get a Heaviside function. And you can also consider it as a convolution between the Heaviside function and the spectral density. So this is basically just the cumulative distribution function associated with the probability distribution we considered just then. And again, this function contains all the information about the spectrum because each jump of the piecewise constant function corresponds to eigenvalue of h. So this function is like a constant almost everywhere, but it has some discontinuity, and each discontinuity corresponds to an eigenvalue of h. It's also monotonously increasing because you're like integrating, right? Integrating something positive. In particular, we're looking for this first jump that corresponds to the ground state energy. And yeah, as Cx is a monotonously increasing function, so that helps us find the first jump because we can just do a binary search. So if C of x is some non-zero value, that means the first jump is to the left of it. Like if C of x is 0, that means the first jump is to the right of it. So we can do a binary search because of that. And very importantly, C of x can be approximated using the Harman test data, so we can actually compute it. So because of all these features, we can use C of x to find the ground state energy. So let me show you some numerical results. So here, this orange dashed line is the exact CDF corresponding to some Hamiltonian. You can see there are it's constant, and then there's a jump. So the first jump corresponds to the ground state energy, and constant jump. So this is another eigenvalue, and you can see it's basically just keeps going like that. And the blue curve is the numerical approximation we compute from the Harman test circuit. You can see there's a large amount of noise, right? But the first jump corresponding ground state energy is resolved very clearly, and that's actually what we want. So we don't care about how much is oscillating here. As long as the jump can be seen, it is good. Let's zoom in around the ground state energy. So this is the ground state energy. You can see the exact CDF takes a jump, whereas our numerical approximation, well, it's continuous. It doesn't jump, but the transition is pretty steep. So there is a transition interval on the order of delta, which roughly corresponds to the resolution of the algorithm, and the height of this jump is at least eta. So basically, that tells you how the precision you need for computing this function. So you need noise to be below eta. Yes.
This is just statistical noise, right?
Yeah, this is just statistical noise. Well, there is a little bit of noise coming from the approximation. So yeah, but that can be made very, very small, like exponentially small.
So could you remind us why did we integrate it from -pi instead of -infinity?
Well, that's simply because you don't have any eigenvalue to the left of -pi. So, yeah. Any other question? Okay.
Oh yeah, did you tell us what the algorithm for that calculation is?
The algorithm for what?
Calculating your approximate Heaviside function there.
Yeah, I'll talk about it next. Right. So we need to. So as long as we can compute the approximate CDF, everything is fine. Right. And so how to do that? So we define this approximate CDF to be as the following. So it's the convolution between the CDF and the modifier. So the CDF itself is already a convolution between the Heaviside function and the spectral density. So the C to the X is a convolution between these three things. And approximation is in the following sense. So the C to the X is lower bounded by C of X minus delta plus epsilon prime, and it's upper bounded by Cx plus delta plus epsilon prime. So what it actually looks like is that, say you have this is your C of X. C to the X is something like, so it, so it may deviate from C to the X if you look at point-wise error. So this is C to the X. You can see, well, if you look at point-wise error, here the error is huge, right? But it doesn't. But it's still. But this kind of approximation still holds because it is the value here is upper bounded by the value here and also here. So this is because we only want to resolve the jump. We don't care what the value actually is. Like
Just half of distance of the graph?
Yeah. Like you can see, like we have these two graphs and they are close to each other on the 2D plane. Yeah. So that's one way of looking at it. And this C to the X is easy to resolve because we can write down its Fourier coefficients, which are just products of m hat, k h hat, and mu hat. So m hat is the modifier, the coefficient of modifier function, which we have already seen. There are only finitely many of them that are non-zero. For this h hat is the Fourier coefficient for the Heaviside function. So it decays very slowly, but it still decays. And that's actually an important fact we are going to use. And this mu hat we can compute from harmonic test circuit. So that's basically how we approximate a CDF. Yeah. And so we could do the approximation like term by term, right? So the C to the X, we write down its Fourier expansion, evaluate each Fourier coefficient separately by evaluating mu hat, but you will never be able to reach Heisenberg limit if you do that because there are like d many of them to evaluate. D is on the order epsilon to the minus 1, so this epsilon gs is the ground state energy precision. And each term will require evolution time that's linear to the absolute value of k. And so k goes from minus d to d. So, right, if you just add everything up, it's going to be epsilon to the minus 2. So you will never reach the Heisenberg limit if you do that. But like we use the third observation we had, which is not all terms are equally important. So we can sum up all the Fourier coefficients here, so if you take absolute value of all the Fourier coefficients to sum them up, like the Fourier coefficient of this m hat is upper bound by 1, simply because this m integrates to 1. And it's like it doesn't have to be positive, but it's almost positive. And the Fourier coefficients of Heaviside function decays like 1 over k. So you have some. So this comes from the Fourier coefficients of Heaviside function, and if you sum them up, you get something that is log in d. But there are linear in d many terms, so that means most of them are very, very small. So that means we don't need to evaluate them one by one. Rather, we can do some kind of importance sampling to resolve the important ones while leave out the unimportant ones. So what we do is that we choose we sample some random variable k with the following distribution. So this big K is equal to k with probability that is just determined by the Fourier coefficients of the modifier function and the Heaviside function. So I need to normalize everything in order to make sure it's a probability distribution. So then this C tilde x can be evaluated in the following way. So we multiply this normalization factor to the expectation value of the mu hat k up to some, like there is a phase factor that needs to be multiplied to it. But a phase factor is fine because it doesn't contribute to the variance. So mu hat k is computed from the Hartman test circuit. So we can just randomly sample this k to be k1, k2, all the way to kns, and compute this thing. So mu hat you get from Hartman test circuit. This data you can just compute classically and take average and then multiply by the normalization factor. So then you can compute the variance, right? So the variance of this thing is upper bounded by 1 because you get a 0-1 output, and this is just a this complex number has modulus 1, and the only thing determining your variance is basically just this normalization factor, and it has magnitude log d. So your variance is basically log d squared, and you're taking n as many samples, so the total variance is like this. Yes?
Maybe I missed this, but can you remind me how fast do the Fourier coefficients of mk and decay? You showed us a picture of mk. I don't think you...
Sorry, mk or hk?
No, mk. But the Fourier coefficients of the...
How does it decay?
Yeah, how fast?
Yeah, so it doesn't decay. Like it's upper bound by 2 pi. Yeah, what decays is the Fourier coefficients for a Heaviside function. It decays like 1 over k, like this. Yeah, so when you sum them up, you sum up things like decaying like 1 over k, and that gives you a log.
So I'm curious, why don't we use something like a Schwartz function, because the Fourier coefficients of Schwartz functions decay like Schwartz functions?
Yeah, so it decays after some point. You can use, say, a Gaussian kernel, right? But then you need some resolution that is on the order epsilon. So basically, after 1 over epsilon, your Fourier coefficients will decay exponentially. But what we actually need is just the first 1 over epsilon, like coefficients, right? So basically, this m hat is already taking care of this kind of truncation. Yeah. And also, this is already log d, so maybe you can make it to constant, but that's a log factor improvement. It may be useful in practice. Yeah, I do think it will be useful in practice if you can make this constant. Yeah, but right now it's sufficient for our goal. Yeah. Any other question? Right. Okay, so then we know how to get the ground state energy from the approximate CDF, and we know how to compute the approximate CDF. So basically, we have the algorithm. So locating the first jump only requires precision eta, which is the lower bound of initial overlap. So therefore, we need the variance to be at most eta squared. So that means the number of samples we need is like this. And if we want to compute the ground state energy to precision epsilon gs, then we need d to be on the order epsilon gs inverse. So the total we just plug it into here. And multiply by OD. So OD is like how long you need to run on average for your Hartman test circuit. And and then you get the final expression for the total runtime. So you can see here, this is epsilon gs inverse. So in this way, you achieve the Heisenberg scaling. I'm hiding the log factors here. And we have this eta to the minus 2 that corresponds to the precision we need for the approximate CDF. Now we can make some comparison. This is textbook's version of QPE. So the runtime is epsilon inverse eta to the minus 2, which is good. And required circuit depth epsilon inverse times eta to the minus 1, which is not so good. It requires a large number of ancillary qubit. So this QEEP is what we have seen. It has at the beginning of this tutorial, so it's like epsilon to the minus 4, which is pretty bad. But circuit depth is good. only requires 1 Angular qubit. And this new method I just described gives you this kind of runtime, epsilon inverse times eta to the minus 2. So it matches what you have in QPE. Circuit depth is epsilon inverse, which is good, and the single Angular qubit. So basically, you have all the nice things we want. But so there are several other algorithms. So if you only care about the total runtime, actually the best thing you can get is epsilon inverse times eta to the minus 1/2, which is proposed in this 2020 paper by Lin and myself. So there's actually a lower bound result that says you cannot do better than this. So this is the optimal method. And for QPE, I only talk about textbook version, but actually you can modify it in several ways that improves the runtime from eta to the minus 2 to eta inverse, and also reduce the number of Angular qubits, as well as the circuit depth. So this algorithm achieves the Heisenberg limit scaling, uses single Angular qubit, and can use imperfect initial state. So that satisfies all the requirements I outlined at the end of the first part of the talk. And this algorithm has been extended in various ways. So far we have been considering mainly the ground state energy, but you can compute observable expectation values as well from a modified circuit, which was proposed in this paper in 2021. So by I think Ridra, one of the authors here, and also I haven't talked about how to implement this e to the minus I tau h. In the original paper, we considered implementing it using Trotter, which they introduced yesterday. But that introduces systematic error, which you need to, if you want to reduce that, you need to increase circuit depth. But there's a way to make the estimation unbiased. So you can reach arbitrarily high precision by only increasing the number of samples rather than increasing the circuit depth. So that requires compiling this e to the minus I tau h in a randomized fashion. So this was proposed in this 2021 paper by Wan, Berta, and Campbell. So far our circuit depth is epsilon inverse, but if there is a spectral gap, which means there's a gap separating the ground state and first excited state, you can further lower the circuit depth to be order delta inverse, where delta is a gap rather than epsilon inverse. So when your precision is much smaller than the gap, then this will help you further reduce the circuit depth. So it was done in this paper. So far I've been considering this Hartman test circuit, but you can add z rotations to the control to this Angular qubit to make it something like singular value processing. Yeah, that will give you a better runtime, which scales like epsilon inverse times eta inverse. But your circuit becomes a little bit more complicated. Also, this Hartman test output is basically gives you a classical signal on which you can do classical signal processing. And one way to do classical signal processing is just to do least squares fitting. So when you have a dominant frequency, which means, say for example, your ground state overlap at the very beginning is larger than 1/2, then maybe instead of locating the lowest frequency, we just try to find a dominant frequency with the largest, largest Fourier coefficient. So we can use a least squares fitting to do that, and it turns out it's very beneficial with large overlap. You can basically reduce the circuit depth as a function of the overlap. As your overlap approaches 1, you can basically arbitrarily reduce the circuit depth. So that was proposed in this 2022 paper by Jianding and Lin. It is shown that the method is, the Hartman test circuit is robust under simple noise models. So that's another good feature of it. And this is what I'm going to talk about next. Yeah, any question at this point?
Yeah, so for the first page, we're talking about the spectral gap. Yeah, I was wondering for example, real quantum manipulated system, and is there any theoretical estimation or empirical estimation for the actual gap between the ground state and the exit state? How is it scaled with respect to the n?
Yeah, so estimating the spectral gap is a very, very hard problem. It is harder than estimating the ground state energy. But I think empirically there are something you can do, but they are not really rigorous results. Yeah, it's very difficult to get to the gap, other than some, say, non-interacting system.
But for gap, you don't get to epsilon accuracy. You get to some module.
Yeah. You only need a lower bound, right? Like it doesn't have to be very accurate. Yeah. But that's still hard.
A different kind of hard.
Yeah, I forgot what the complexity class it is, but it's worse than QMA at least.
So if your ground state is degenerate, this is still okay, like in this?
Yeah, if you only want to get ground state energy, it's still okay. Yeah. Yes.
So you did this importance sampling where like the probability was kind of proportional to the magnitude of the Fourier coefficient. So I guess if I just naively tried to only sample, like you just pick the wave numbers, like the smallest wave numbers, because I know those have the largest Fourier coefficient. Like how does that compare to, like why do I need to actually randomly sample if I know the probabilities already for which ones will be the largest?
You mean just throw away those with small probability?
Yeah, like why even allow the option to, I mean, maybe there's something.
Maybe that will do better, maybe that will do worse, I don't really know, but if you do it the way you're describing, you will introduce a systematic error, right? But here, like if you look at the expectation, it doesn't have any error. You only need to analyze the variance. So if you do it the way you describe, you need to analyze the error carefully. I don't know how good that will be. Yeah, maybe it will be pretty good, but yeah, just don't really know. Any other question? Okay. So now let's look at some simple noise model. So we consider only the simplest possible noise model, which is not realistic at all, but it's so simple that we can analyze it. So that's why we consider it. In a Heisenberg test circuit, we consider the following noise model. So each time we apply this control time evolution, then with probability 1 minus e to the minus alpha tau, the system decoheres into the maximally mixed state. So if you don't know what that is, it doesn't matter, because you can just interpret it as like you lose all the information in your circuit. Like, basically everything is gone. But with probability e to the minus alpha tau, the state will still be what it should be. So this is not really realistic when we talk about quantum algorithm, but in some random circuit model, people prove that indeed, as you increase the circuit depth, the noise converges to this kind of white noise. So if this is a noise model in your algorithm, then output m hat, which is this 0, 1 thing we read out from the Heisenberg test circuit, will satisfy the following. So if you take the expectation, it's going to be, this is the original value, the expectation of the unitary e to the minus I ht, multiplied by something that is exponentially decaying, right? So this is not good because your signal is exponentially decaying, but the good thing is that we know what it looks like. So what we can do is just multiply it back. So if we want to estimate this thing, we just do e to the alpha t times this expectation value. So that's a simple error mitigation strategy. So it is acceptable if alpha is not too large compared to the t you need to run, right? Like if you want to go to some t, your alpha is 1 over t, then this factor is pretty good. It's just some constant. Yes.
Is the assumption that you've done some process to determine alpha, I guess, or like, in practice, right? You wouldn't know alpha from your computer.
Yeah, exactly. So yeah, you need to determine alpha in some way by say fitting. Like, but that's separate from your algorithm, right? Like you're determining a noise model. So yeah, but yeah, indeed, you need some knowledge of alpha.
Also, maybe write down the definition of the channel, so for people.
So yeah, so basically, your error channel it takes a quantum state rho to so with this much probability, it's still rho, but with this much probability, it becomes a maximally mixed state, which is the uniform distribution over all bit strings, basically. But if you're familiar with the density operator formalism, this will make sense to you. If you're not familiar, it will probably not make sense. But but I don't think I have enough time to talk about that.
Just a question, wouldn't it be more systematic to use this general Lindblad form for quantum Markov processes?
You mean consider more general error model than?
Right, I mean where you have this IH in front and the noise later.
Yeah. I think that's much more realistic than this. But then the analysis becomes non-trivial. So ideally one would want some way to turn an arbitrary error model into something like this. It's not always clear how to do that. Right? But the good thing is here that if you consider a random circuit, it will actually turn the kind of error model you described into this error model. So.
Also, even with this very simple error model, the QPE completely fails. It's almost beyond silly. It's not obvious you can read the information from QPE circuit as well.
Right. So that's what I'm going to discuss next. So here you can do error mitigation by just multiplying a number. But for QPE, what will happen? So in textbook version of QPE, we use the same error model. And so this error model is easy to analyze because maximally mixed stays invariant under unitary operation. So because this is an identity operator, right? So if you plug U and the U dagger on both sides, it will still remain identity. So if you act any unitary on it, it will not change. So what happens here is that the ancilla register has, so when you do so when you do measurement, the ancilla register has this much probability of returning a uniformly random bit string. So when you look at output probability, it looks like this. So this is the output probability of getting an energy measurement that takes this value in a noisy circuit. So it is equal to the probability of getting the same measurement in a noiseless circuit multiplied by this factor that is exponentially decaying in 2 to the r, where r is the number of ancilla qubits and 2 to the r is how long you need to evolve, plus this uniform distribution multiplied by this factor, which is, so this is basically the probability of an error occurring. This is probability of no error occurring, and this 2 to the r comes from the uniform distribution over all bit strings. But if you remember what we were doing for QPE when we try to find the ground state, is that we do multiple energy measurement, take the minimum, right? And but because we're taking the minimum, with large probability, a bit string coming from here, from the uniform distribution, will be the minimum, right? So that means it's possible for any bit string to show up, and with large probability, you will end up with a bit string that's lower than your ground state energy. So the result is totally disastrous. Like you basically just get something random, and there's no way to mitigate it. Yes.
But shouldn't these random bit strings just be some sort of noise, and my signal still be on top if I repeat it often enough? So
yeah. Then you need to resolve the whole distribution in order to see that. Right? It's just not a single point. So this kind of noise robustness actually makes it suitable for early fault-tolerant quantum computers. But what we never expected is that it was actually implemented on a current device. So this is an experiment done by Riverline on superconducting qubits. So they implemented a modified version of this Harman test-based algorithm, and this is CDF they computed from actual hardware. So you see it's like oscillating like crazy here, but the jump is very clearly resolved. So they were able to compute the ground state energy of small molecule from it. So the molecules are very small. They do some kind of embedding to make sure the active space is even smaller. So with up to 4 spatial orbitals, which means 8 spin orbitals, they were able to compute the ground state energy to 0.1 millihartree. So compared to classical computer, this kind of computation is trivial because you can do that very simply on your laptop. But on the current hardware, I think this is very amazing result because this kind of, so this is already 1 order of magnitude below the chemical accuracy, right? So it's very difficult to get to this high precision. And actually, in their paper, at least, they claim that you cannot do so with QPE. Right? This is already, you cannot do so with VQE. So this is already surpassing the precision you can get with variational algorithms. So they use a bunch of techniques to make this happen, including variational compilation of the time evolution operator. So they didn't just do Chorder. They used some very expensive procedure to get the low depth circuit to actually implement a time evolution operator. And they also use a better Fourier coefficients than what I just described. So the version I give you the correct scaling, but yeah, they can do something even better, but with roughly the same scaling out to log factor. And they use a lot of error mitigation to make sure you get to the signal rather than noise. Yeah, so, and we can compare with some previous implementation of quantum phase estimation. So this was from 2016. So they implemented quantum phase estimation experimentally, and you can see those blue dots are the energy you get by running quantum phase estimation. So comparing to the exact value, the order is the error is on the order of 0.1 hartree, right? So here is 0.1 millihartree. So it's there's huge improvement compared to the previous state of the art. Yes.
Is there a reason why the variance in the phase estimation energies gets higher as you approach this point where the bond length is I guess you're reaching the dissociation point of the bond. I guess why is
you mean here? Why is it going up?
Yeah. I guess when you reach this kind of when you're outside the potential, I guess, or outside the well, the variance of that energy seems to go up with phase estimation. Is there some?
Yeah.
Maybe the initial overlap gets worse.
Well, they're using Hartree Fock, right? So the initial, so this is hydrogen molecule, I think. This is something more complicated than that. And the overlap here is 0.6. I think for hydrogen, the overlap is probably going to be 0.9 plus. So the overlap shouldn't get smaller.
There's the exact, right? I mean, there's a Cousin-Fisher point. So the Hartree Fock becomes pretty bad.
Okay, I see. Yeah, so that may be the reason. Like they're probably getting.
I don't know their overlap.
Yeah, but I wouldn't imagine it to be too small. Like
it could be because the RCAF, the energy shoots to the roof. The UHF gets you the right energy, but the wrong spin, so the overlap must be wrong.
Okay, I see. Yeah, that may be possible. Then they're maybe just getting an excited state energy. Yeah, but then the energy also goes down, right? So it's actually not a variational algorithm, so you don't. So that's basically the end of my talk. Let me conclude. So for early fault-tolerant quantum computers, we may need to optimize for a number of metrics, including the circuit depth, number of qubits, and error robustness, rather than just runtime. So there are maybe other things you need to optimize for, especially if you take into consideration the kind of error correcting code you're using and your architecture, right? So I think these are all interesting problems to consider, like if you want to do anything practical. And it is possible to optimize for these metrics while keeping the Heisenberg limit in scaling, which is very important for achieving the kind of precision we care about in quantum chemistry. And we do not know what the first fault-tolerant quantum computer will be like, but here we're proposing a framework of designing algorithms, and you may just, like when you have the quantum computer, you may judge what metrics are important, what metrics less important, and that becomes a multi-objective optimization problem, and you may just use this framework to design the quantum algorithm that best fit into this framework. So yeah, with that, I want to Thank you for your attention, and I'll be happy to take questions.